In the last video, I introduced the idea of electric potential energy. Now, in this video, I'm going to be introducing the electric potential. Now, although the names sound disgustingly similar, there are actually two different ideas, two different concepts that are there is some relation between them, but they are not the same thing. Um, this is this is actually quite confusing terminology. Unfortunately, it's standard. Within the physics community, there's a shift away from calling it the electric potential and starting to refer to it according to the unit that's measured by the volt. Call it a voltage. This is also kind of dumb. That would be just like calling force newtonage, which sounds really silly. But you'll in here you'll be hearing me use probably about a 50-50 split between saying electric potential and voltage, just because both terms are still in wide use. So if someone says the potential or the electric potential without the word energy, they always mean this idea. If they mean the electric potential energy, they will always say the word energy with it. So with that as a bit of, and just to clarify where this is coming from, the potential here in electric potential actually comes from some math jargon, whereas in potential energy, it's the idea is the potential to do work. So it's a collision of math and physics jargon that shows up right here. Anyway, with all of that, we will go ahead and define the electric potential or the voltage. The symbol for it is a capital V. Remember, the triple equal sign means by definition. So this is associated with a location. So say at this location right here, I decide to stick a charge Q there. It will have some electric potential. There will be some electric potential energy associated with how this charge is interacting with all the other charges everywhere. We then take whatever charge I put there and divide it back out. Similar kind of idea to what we did with the electric field. So as far as the units of this goes, this is joules, this is coulombs. We will the unit of electric potential is the volt, and 1 volt is 1 joule per coulomb. And yes, I know the symbol for volt is also a capital V. I usually try to make it the unit without the little bars on top and the voltage or the electric potential with the little bars on top, because otherwise you're going to get silly looking things like people writing V equals 42V. And when you see something annoying like this first V here, which I'll always put little bars on, or try to anyway, this is the electric potential, which we also call the voltage. And this is the unit here, which is the volt. Yeah, I know. All I can say is please don't shoot the messenger on this one. All of this is incredibly standard notation. It's what everybody uses. In languages that aren't English, it isn't as bad, but this is what we have to deal with. So following this through here, I will make a quick aside and mention how physicists usually express the units of electric field. So previously I introduced that we would say that the electric field is 1 Newton per Coulomb, and you can absolutely write that and it is no problem whatsoever. However, what we usually end up saying is we'll say it's a volt per meter. And so let me just work through the unit arithmetic of that. So 1 volt, that is a 1 joule per coulomb. So now if I divide that by meters here, this is going to be 1 joule per coulomb meter, like that. A joule is a Newton times a meter. So you're left with the Newton per coulomb. So both are in wide use. It's more common, I would say, for people to say volt per meter. And this has to do with the actual technical issues of how you would measure a electric field strength. Usually what you do is you measure the electric potential difference between 2 points, the voltage difference between 2 points, and divide by that distance. And you measure that voltage using a device called a voltmeter. So the display reads volts, you know how far apart your probes are. It's just natural to call it volts per meter. You'll probably hear me flip back and forth, being pretty interchangeable with it, and they are interchangeable. A Newton per coulomb is a volt per meter. All right, so now back to electric potential, or voltage. So leveraging off of the results that we had before, for a uniform electric field, remember we said that the potential energy difference was QEX. Okay, if I divide by the Q, I'll get that the difference in voltage between 2 points along an electric field line will be the electric field strength times X. I'm not going to get too strung out about plus or minus signs, so I'm just going to throw an absolute value around it. But basically the idea is, say over here, this is my electric field. Then I look at this point here, parallel to it. This distance is X. What we'll see here is that electric field lines always run from high voltage to low voltage. And the difference between these two voltages, so if we say this is V2 and this is V1 here, this would be my V2 minus V1. That's going to be equal to the electric field strength times that distance X. Okay. And similarly for a point charge, we can say the voltage associated with some point in space. So let's say I have a point charge Q here, and I want to know what's the voltage there if I am some distance r away from the charge. Following this same definition, the potential energy would be K times Q times some charge I pretend to put here over R, and then I divide by that charge I pretended to put over there, and I will be left with the voltage at this location being KQ over R. And again, as a carryover, because of the calculus-based considerations we had to do for the equation for electric potential energy, we're also required to say that if we are infinitely far away from this charge, that we are setting the voltage equal to 0 there. And again, it's the same deal. We're actually free to always add a constant to our voltage, which when we analyze electric circuits will be a trick we'll use a lot. Okay. Now, where a lot of the utility of this is going to come from, or a lot of the utility we'll get out of this, is in later videos. We'll see how what we can do is we can figure out how to come up with a map of voltages across space. And because voltages are just scalar numbers, it's easier math. And then it turns out that looking at this map, we'll be able to deduce the electric fields, which are vectors. So this turns out that this will be one of those things that will ultimately make the math of figuring out electric fields easier for us. But for now, I'm going to just kind of go over a few other things that get associated with this. One of these is a unit of energy that shows up a lot in atomic and nuclear and high energy particle physics. Basically, it shows up in chemistry. Basically, it's anything that you'll do in the world of the really small. So in the world of the really small, so this is a unit of energy here. We have a unit of energy called the electron volt. You write EV like this, or sorry, like that. So this is, but you read it as electron volt. Even though this isn't quite right, because E is not the charge on the electron, that would be negative E. It's the fundamental, but it comes off the tongue a lot easier than saying something silly like fundamental quantum of electric charge volt. That almost defeats the whole purpose. What this actually is, this E is literally the fundamental quantum of electric charge, E. And it's times 1 volt. Okay, what does that get you? Well, it turns out it's a compact way of writing E. The fundamental quantum charge is 1.6 times 10 to the negative 19 coulombs. And we can remember that a volt is a joule per coulomb. So this is a way of writing in units of 1.6 times 10 to the negative 19 joules. All right, so where that's useful is at the atomic scale. Energies that you'll be typically worrying about are maybe from about 1,000th of a EV to 1,000 EV. So it's a lot nicer than having to carry all these 10 to the negative 19s in front of joules and everything like that. So it shows up a lot for that kind of thing. However, it also shows up for being for wanting to be easier to do certain kinds of problems. So as an example here, let's take a look at a device called an electron gun. So what an electron gun is you have a filament here, just like you would have an old style light bulb before we switched all to LED bulbs. And you pass a bit of current, electric current, through the filament. What will happen is that there will be enough thermal energy that some electrons we always say boil off. It's not technically boiling, but just basically they get so hot that they literally just jump off the filament. We call it boiling off, but it's not really the same thing as boiling water. And then what you do is you put this between a couple of plates, metal plates like so. Oop. There we go. And you'll go ahead and hook this up to a battery. And sometimes literally an actual battery, other times a power supply. Batteries have the advantage of having very stable voltages, so they still get used a lot for this kind of work. Anyway, we put the negative terminal of the battery there, positive terminal there. All right, let's say this is 1,000, just to kind of make this concrete, let's say this is 1,000 volts. Electric potential difference here. All right, so this means that the voltage here is 1,000 volts higher than there. Let's get that filament a little closer to that plate. Now, on the positively charged plate, you'll drill a tiny little hole. So now what will happen is some electron will jump off of the filament here. So the idea here is this plate will have a negative charge, this will have a positive charge. So the electrons will be repelled away from this negative plate, attracted towards this positive plate. Now most of them will get absorbed onto this plate because they hit the plate, but the occasional few of them will fly through the little hole that you made. And for those that fly through the hole, what I would like to know is what is my final speed expressed as a fraction of the speed of light. Now, the reason we do these kind of calculations is that a lot of times it's a lot of situations you can still not have to take into account Einstein's theory of special relativity. And so a lot of times what physicists will do is they'll do a calculation using Newtonian methods, cross their fingers that they don't have to use relativity, and then at the end they check how fast was everything going. And as long as it's no more than a few percent of the speed of light, usually that's good enough, and so retroactively you can justify the fact that you did it with Newtonian mechanics. On the other hand, if you get either a high fraction of the speed of light or the nonsense answer of faster than the speed of light, then you curse your luck and you realize that you have more math ahead of you because you'll have to use relativity, which is coming up. Well, anyway, we can go ahead and conserve energy on this. So the change in the potential energy will be equal to within plus and minus signs will be the change in the kinetic energy. So this is going to be my charge, delta V. And I dropped the minus sign from the electron just because I'm working an absolute value here. And by same logic here, my final kinetic energy will be 1/2 mv squared, and the initial was 0 because it was at rest. So, all right, I can rearrange this and get that my final speed is 2e delta v over m. Now, here's where the genius of this unit comes in. So when you start expressing masses in terms of these EVs as well. So the mass of the electrons we've seen before, you can remember by thinking call 911. So call 9.1, so it's 9.11 times 10 to the negative 31 kilograms. But here, I'll leave it for you to grind out the math to show it to yourself. You can also express this as 511 kiloelectron volts per c squared, where this is a lowercase c, this is the speed of light squared. And this is coming from using E equals mc squared, the one physics equation you probably knew before you ever took any physics, which we will be getting to. Anyway, the whole point here is just leave this E here. We'll go ahead and put in our voltage difference. It's 1,000 volts. And then we'll write in my mass. I'll have to get the kilo out, so it'll be 511,000 EV per c squared. Now this E literally is this physical constant E, and so the unit is set up so that you can actually cancel the constant out like that. Awesome, huh? And then similarly here I can cancel out my volts, and so I'm left with something that's going to be the square root of 1 over c squared. Well, 1 over c squared is c squared. Take square root of that, that's c. And so when you go ahead and do the math on this, you get that our electron flying out of the electron gun is going at 0.0626 times the speed of light. 6.3% of the speed of light is not typically a relativistic number unless you're being insanely fussy in your calculations. So someone looking at this will say, okay, I can get away with doing a Newtonian treatment. Plus, with these units, it's just plain easier. You don't have to do as many gacky unit conversions and stuff like that. Now, one of the other things I just kind of want to get into as a lead in to future videos where we're thinking about how to get the electric field from potential is there's going to be many different ways to represent representations of the voltage. There are many different forms. So for instance here, let's just say I have a point charge. So we've already seen if I have a point charge plus Q, the voltage is going to be KQ over R. Now let's think about what that looks like. One thing I could do is I could just make a graph. I could plot the voltage as a function of radius, and it will fall off as 1 over R. So that's one way I could do it. And I'm about to attempt to try to draw in 3D, so sorry, all I can say is I tried really hard. So let's say another way I could do this is I could draw, so this is a graph, I could draw what are called the equipotential surfaces. So this is a potential graph. So what will be happening in 3D here is, let me use, let's say gray here. Gray. So what I'm doing is just saying anywhere on this sphere, the equa means the same, equipotential. Sorry about that. Potential. So everywhere on this surface, the voltage is the same. Then I can draw another surface that's bigger, like this. This will be a different voltage. So this will be a higher voltage here because we're closer. This will be a lower voltage. And then I could have something in between, and I'm going to draw it closer to the higher than the lower. Because usually what you do is you try to make it like the same number of volts different. So the surfaces will be packed more closely together, closer to the charge, and farther out the spacing will get bigger. Now you can see just how well this is working trying to draw this in 3D. So a lot of times what people do instead of that is they'll just draw what's called a contour map. So a contour map, what they'll do is now here we're drawing a bunch of circles. So this is a contour map. And what you can imagine we've done here is I've put a plane through my equipotential surface and just seen where the contours cross, and then I just draw that much. So basically, physicists do this sort of thing all the time. We draw these circles like this. So this is a higher voltage here. This is a lower voltage there for our positive charge. So physicists will draw something like this, and you'll see the concentric circles, but what they'll be visualizing is these nested spheres. So we do a lot of this sort of thing where we're drawing cross-section and assume the person looking at the cross-section will extrapolate out what the 3D image is. Now, another one that you see sometimes, it doesn't show up a lot unless you are having a computer draw it for you, is you might take this, whatever plane that we cut through here to get this, you could instead plot the voltage as a function of, say, X and Y like this, and you'll get something that's kind of looks like that. Sort of a volcano looking kind of thing. This is an elevation graph representation. And with practice, the idea is basically you look at any one of these, whichever you think is the most useful, and you should be able to ultimately visualize the rest of these. Now, where this is going to come in particularly useful, so if you've ever done any hiking, when you do hiking, the maps that you carry along, or if you're using a phone app, will be displayed in your phone app. They'll draw what are called elevation contours. So they'll draw a line everywhere at the same altitude. And so the idea here is just like if going from here to here, this is a higher voltage. In a certain sense, I'm going uphill in elevation. We'll see ultimately that the electric field lines will actually be rolling downhill, but that's for a later treatment. All right, so with that, I'll catch you in the next video. Have a good one.